In this segment, we'll talk about how Gaussian method works. We'll talk about the background of Gaussian method so far as the steps which are involved in it is concerned. So let's go and do that. Now, Gaussian method is basically a way to solve simultaneous linear equations which can be written in the form of Ax equal to C, where A is the coefficient matrix, C is the right-hand side vector, and X is sometimes called the solution vector, or it might be called the unknown vector. Now, for Gaussian method, there are two steps. One is forward elimination, and the second one is followed by back substitution. What you do in forward elimination is basically to take the coefficient matrix and you reduce it, take the equations and you reduce it such that the coefficient matrix becomes upper triangular. In the back substitution, what you do is you then solve those equations now starting from the last equation. That's why it's called back substitution. But we will get familiar with what we meant by that once we start talking about the individual steps, the forward elimination step and the back substitution step. Now, the goal of forward elimination is to transform the coefficient matrix into an upper triangular matrix. So I'm going to show you an example first because that's a better way of trying to teach you this stuff. Let's suppose I have three equations, three unknowns like this one. And what I'm going to do is I'm going to eventually manipulate these equations by doing some addition, subtraction, multiplication, and divisions. And what I'm going to end up with is a set of equations like this one here, right here. So the solution to this set of equations is same as the solution to this set of equations because they have been found by simply doing some manipulations of addition, multiplication, addition, division, and subtraction, which are allowed by matrix manipulation. So that the solution stays the same. And what you are basically seeing is that the coefficient matrix is turning out to be an upper triangular matrix, which is pretty evident from the zeros which I get below the diagonal. And what that does is that it allows you to now be able to use the back substitution steps which I was talking to you about, one equation at a time and one unknown at a time. So if you look at this one here, by being able to convert this into an upper triangular matrix, you are able to now solve only one equation, one unknown at a time, because if you look at this equation, there is x3 is the only unknown. Now if you look at this equation right here, you might think that here there are two unknowns, x2 and x3, but you just found out x3. So there's only one unknown, which is x of 2. Now here, then you start with the third last equation, which in this case is the first equation, and here you might say, hey, in that equation I have three unknowns, x1, x2, and x3, but you just found out x2, you just found out x3, so there's only one unknown in that equation. So the reason why you are going from here to here, going from the coefficient matrix which is given to you to a coefficient matrix which is upper triangular is mainly to be able to solve one equation, one unknown at a time by using the steps of back substitution. So now let's go and look at the algorithm for forward elimination. So these are the steps, these are the equations which are given to you. So let's suppose somebody is giving you n equations and somebody is giving you n unknowns. The unknowns are x1, x2, x3, x of n, so on and so forth. These a's which you have here are the elements of the coefficient matrix, and b's of 1s and so on and so forth, they are the elements of the right-hand side vector. And one of the things, again, you got to understand there are n minus 1 steps of forward elimination because each step within the forward elimination is used to make certain things to be 0 so as to be able to convert the coefficient matrix into an upper triangular matrix. What do we mean by that is that what we're going to do is in order to be able to make, this is the second row. No, this is the first row. So we're going to take the first row here. So we're going to take the first row here. Let me go back here. If you see this one right here, what I'm going to do in my first step of forward elimination is that I want to make this to be 0 and all of the elements which are in the first column below the second row and below, I want to make them to be 0. And now what I can do is in order to be able to make them to be 0, I can divide by this element ace of 1, 1 and multiply it by ace of 2, 1, let's suppose, and use that multiplier on this particular equation. And what that's going to do is I'm going to get ace of 2, 1 from there, and I can subtract it from there to make this to be 0. And I'll continue the same process till the last element. So I'm going to show you in the next slide, which I was just showing it to you. That's what I'm going to do. So I'm taking the first row, and I'm going to multiply by ace of 2, 1 divided by ace of 1, 1. Now, how do I come up with this is because I know that this is ace of 1, 1. If I divide by ace of 1, 1, I get 1. And then if I multiply by ace of 2, 1, then the coefficient of this one will turn to be ace of 2, 1. And now if I subtract this particular equation from the second equation, the coefficient of x of 1 is going to become 0. So let's look at that. So this is what's going to happen. This is the equation which I get. This is the second row which I have, or the second equation which I have. This is the equation which I get by multiplying the first row by ace of 2, 1 divided by ace of 1, 1. And you can see that now the coefficient of x of 1 and the coefficient of x of 1 is the same. So when I subtract, I don't have any x of 1 terms. The coefficient of x of 1 terms is 0, but these terms of course change, and hence I get the second equation to be something like this. I use this prime business here to be able to tell you that, hey, this coefficient has changed, or this this element has changed. But the main thing to understand is that there is no x of 1 term in the second equation anymore. Now what's going to happen is that I can do the same thing for all of the elements in the first column now below the first row. I just made this to be 0. I'll make this to be 0x1 plus, and then I'll have 0x1 plus, and the last equation also I'll have 0x1 plus. So all the elements of the first column except for the first row have been made to be 0 in the first step of forward elimination. So that's why it's very important to understand this is the end of the first step of forward elimination. If you have n equations, you'll have n minus 1 steps of forward elimination which you'll have to conduct. If you have, let's suppose, 5 equations, you'll have 4 steps to conduct. In the example which I showed you, there were 3 equations, 3 unknowns, so I had to conduct 2 steps of forward elimination. So let's go and see now what I have to do next. So what I'll have to do next is that I'll have to take this as my pivot equation, pivot element, and make this to be 0 and all of the elements which are below here to be 0 right there. So what that means is that I'll have to divide by a22 prime. Let's suppose if I want to make this to be 0, I'll have to divide by a22 prime and multiply it by a32 prime. So by doing that, so I'll take this equation and I'll multiply it by this this multiplier, and then when I subtract it from this particular equation, I'll get a 0 there. And you want to use the same methodology to make every element below the second row in the second column to be 0. And this is what you're going to end up with. So if you look at this particular portion of the equations right here, they are all going to become 0 by following the procedure which I talked about. So you don't see any elements of x2 here. The coefficients are all 0. So that's the end of the step 2. So you're very well seeing that how you have to conduct each step for each column. So the first step of forward elimination was corresponding to the first column. The second step of forward elimination made the second row, made the second column below the second row to be 0. The third step of forward elimination will make everything below the third row in the third column to be 0. So you can see algorithmically how this can be written in a loop to be able to conduct these forward elimination steps. So as we said that there are going to be n minus 1 steps of forward elimination, and this is what I'm going to be obtaining at the end of the forward elimination steps. And you can see that I get zeros all the way right here, I get zeros all the way right there, then zeros all the way here, and this is turning out to be that if I write this in a coefficient in a matrix form, that the coefficient matrix will turn out to be an upper triangular matrix. And that's what I'm showing you here, that we are writing down the equations we get at the end of the forward elimination steps, all the n minus 1 steps in the matrix form, and you are getting an upper triangular matrix right here because all of these elements are 0. Now pay special attention to these primes which I am showing you right here. This shows you that how many times the A element has changed, because in the first step of forward elimination you find out that this element will change and then it is no longer used. So that's why you find out is a double prime right here, telling you that that particular element is changing twice. It's just to show you that it's not the same element which you have in the previous step. And you can very well see that the last element, last row, last column element will change n minus 1 times. And same is the case here. This right hand side number element changes once. This right hand side number element changes twice, and this number changes n minus 1 times because you're going through those n minus 1 steps of forward elimination for the last row.